Good afternoon, everybody. My name is Valeria Fioravanti, and I'm from the University of Bremen, where I'm going to show you here are the results obtained applying our infrared quadruple wavelength sensor for studying biopsy samples. And it's important for me to underline that these results have been obtained in collaboration with the Medical University of Vienna, which is partner within the European project I belong to. So, first, overview of the presentation. I want to show you first which are the motivation and the aim behind our research project. Then I will explain how the biopsies are prepared for infrared analysis. I will describe then how the infrared sensor looks like and which is the sensing method behind. Then I'll go over the results obtained, conclusions, and future plans. So, the aim is to certain the presence of cancer cells in a biopsy sample by using our special infrared sensor, which is based on the determination of the CH2 symmetric, of the CH2 stretch ratio, like I will explain you in the coming slides. So we are mainly focused on studying the vibrational spectra of the CH2 molecule, which seems to be a very promising fingerprint for monitoring the health state of cells, tissues, and carcinogenesis. So, why do you want to do it? The reason is that still currently the most used and standard investigation method for cancer detection is based on visual inspection. So it means that the pathologist, after removing the suspicious tissues from the patients and stain it, look at it under the microscope or by using their infrared imaging or confocal microscope or stuff like that. But the point is that still it's a visual inspection. So it means that it can be it's an objective kind of investigation, and as several statistical analysis has proved in the last years, it can lead to false positive and negative results. So in discrepancies in determining the presence of tumor in some biopsies. So in order to prevent misdiagnosis and in order to avoid the use of any contrast agents, because it seems that there's not, especially for melanoma, universally accepted co-strength agents, so stain agents for recognize the morphology of the cells. So we want to we have developed this kind of sensor, which is very easy, as I show you. It's made of very easy and simple elements. Is that time saving, it's a very fast machine, cost effective, and easy to use. So what we want to do is just to support medical doctors in their medical investigation. So we analyze biopsies taken from normal skin and primary melanomas. And the biopsy preparation is based on freezing. So the pathologist providing us the sample uses to get the sample, the tissue from the patient, and then freeze it into liquid nitrogen, and then cut it into several sections. Each section has a thickness of 20 micrometers. So some of these sections are then stained and put on glass slides for being analyzed with standard histopathological methods, and the other unstained sections are here put on calcium fluoride slides. Calcium fluoride is a kind of material which is transparent to the infrared. And since we want to perform infrared spectroscopy analysis, it perfectly fits with our aim. So, and now referring to this skin sketch here at the top of the slide, the doctor uses to cut the sample vertically. So it means that all of these sections will contain the epidermis and part of the dermis, so several layers of the skin. So what makes our sensor very special is that instead of recording the whole infrared spectra like complex and competitive infrared techniques that do, we just focus in this region. Why? The reason is because here there's the CH2 absorption portion of the spectra, and from previous studies performed in the early 90s by using Fourier infrared spectroscopy, has been noticed that cancer tissues show different height in these peaks, respect to the correspective healthy tissue. So what we have done was to calculate the ratio between the Th2 symmetric absorbance and the Th2 antisymmetric absorbance, and see if it can be used as a valid biomarker for recognized cancers. And the answer was yes, maybe. So from preliminary results performed over cell lines, we noticed that cancerous cells showed higher Th2 stretch ratio values with respect to normal cells. So that we want to go ahead and see if it can be suited also for studying biopsies. So step back in measurement principle. Since we want to measure just this ratio, we don't need to collect the uniform spectra in this range. What we need are just 4 wavelengths. So the extreme wavelengths are used to calculate the baseline, so as a reference point, and then the other 2 wavelengths are used to calculate the ratio. So this is at the end what we have from our results. So absorbance of 4 specific and functional wavelengths, 2 for the baseline correction, and the other 2 for calculating the ratio. And here you can see in the top the results from one of the melanoma that we analyzed. Well, so how the sensor looks like? We have infrared sources, 2 pulse with infrared LEDs with initial peaks at 3.4 and 3.55 micrometers. Then we have narrow bandpass filters for selecting 2 wavelengths from each LED. So that means 4 wavelengths in total. Then optical system to guide the light into the sample. And here you can see here the sample holder. And then a photodiode to collect the light transmitted through the sample. So here it's shown how our LEDs work, so alternatively. And they are set in order to pulse at a frequency of 2 kilohertz. The width of a single pulse is 10 microseconds. And within these 10 microseconds, we used to perform 20 measurements, to take 20 sample points. So it means 1 measurement every 0.5 microseconds, so that for a total sample rate of 2 million records per second. And despite the huge amount of data that we collect, the overall measurement time to measure just one spot over the biopsies takes just tenths of seconds. So once we fix the biopsy on the calcium fluoride light, we used to collect at least and to analyze at least 3 spots over the biopsies, and a single spot is recorded 4 times with our infrared sensor. The size of the light beam here is 1.5 millimeters in diameter, and this is something that we are trying to decrease. So, well, keeping in mind how the sensing system works and how do we perform the measurements, let's go over the results. Here, first, we wanted to prove the validity of the results coming out from our infrared sensor. So we wanted to compare them with the results obtained by standard histopathological analysis here, and coming from Fourier transform infrared spectroscopy, that is a very consolidated and valid infrared spectroscopic technique. So, in the left side, you can see here a picture of the same normal skin sample that has been analyzed investigated by our pathologist. So here in the right side, you can see the thin layer of epidermis, and then here a thick dermis. In the middle, here at the screen, you see the Ch2 stretch ratio map collected by using the FTIR. So, as you can see, is that the ratio here is ranging between 0.1 and 0.2 in a scale between 0.1 and 0.4. The same kind of values have been obtained by applying our infrared sensor. Let's see what happens if you analyze melanoma samples. So, well, here in the left side, you see again a same picture of a melanoma, and pathologists here recognized epidermis, the thicker epidermis, and the dermis. But here, the basal membrane separating the two layers is not clearly visible, as in the previous case, because cancer cells have invaded both the epidermis and the dermis. But the basal thickness of the sample, exactly, I don't remember how much it was, but it was not so high, since here the pathologists recognized an area with healthy tissue containing just fibroblasts. And the excess results have been obtained using the FTIR. So we have here an healthy region of the tissue, which shows ratio, threat ratio of 0.1, 0.2, but it's surrounded by areas showing higher threat ratio values between 0.3 and 0.4. So higher than the one that I showed you before in the case of normal skin. And performing the same analysis with the infrared sensor, you can see the results are really comparable. So when we have proved the potential of our method and the validity, that we collect several data sets from several normal skin samples and from several melanoma samples in the second row. So the trend seems to be always the same. So lower values for in the case of normal and healthy tissue, and higher values of almost a factor of 2 in case of melanoma samples. So, in conclusion, we can state that our infrared quadruple wavelength sensor can be used to determine presence of tumor cells within biopsies. And this is a very cost-effective and time-saving machine. And again, it's easy to use. And what we want to do is to create a product, portable product to help medical doctors in their diagnosis. And by comparing all the 3 investigation methods that I mentioned and that I show you, we found a very strong and very strong agreement with say. And as next steps, what we want to do is to increase the resolution of our sensor by reducing the spot size of the light beam. In this way, we will be able to analyze smaller spots and exactly target the exact area of the biopsies that we want to measure or that we want to look at. And finally, we want to see if there's a correlation between the variation of the CH2 stretch ratio values within the melanoma samples and the stage of tumor. So, applying our infrared sensors, maybe there is also the possibility to discriminate between different stages of tumor. We hope that it works. Thanks for your attention.